All right, in our final video for section 1.2, we're going to talk about some of the different properties of the definite integral, and we're going to talk about kind of a little bit about why they're true, and we're going to use them in an example. So we're going to start by thinking about some integrable functions, f of x and g of x. Remember that this word integrable means able to be integrated. It means that the integral exists. Since the integral is defined by a limit, it's not true that every function is integrable. Some limits certainly don't exist. But most of the ones, well, really everything that we're working with in this class will be integrable. We're also going to have some constants, a, b, and c, which are real numbers. So what we want to first think about is this integral from a to a. So this maybe seems like a strange sort of thing. So far, we've been looking at functions which you can integrate on some interval from a to b. But if we have some a value and we're thinking about how much area is under the curve between the x values of a and a, again, we're getting kind of this vertical line here. And we know that vertical lines have an area of 0 because they have base width equal to 0. So if we're going from a to a here, there's no width, so this thing certainly can't have an area. 0 times whatever the height is there is going to be 0. So our first property is that the integral from a to a of any function at all is always going to be 0. If the upper and the lower limit of integration are the same, there's no area. The second property that we're going to be looking at is more of a definition than a property. It says that the integral from b to a of f of x dx is going to be minus the integral from a to b of f of x dx. So what this is really telling us how to do is it's not telling us anything about areas that we already know, but it's instead saying that if you want to compute the integral from, let's say, 1 to 0 of f of x dx, this is normally a strange kind of thing to write down, since we would normally put the 1 on top and the 0 on bottom, since 0 is less than 1. It's telling us that this is going to be equal to the negative integral from 0 to 1 of f of x dx. It shouldn't be entirely clear why this is right now, why integrating kind of in the backwards direction should make your area negative, but it's going to turn out that this gives the integral some nice properties later on that are going to make a lot of problems easier. So we're going to work with this for now. Part C is asking us about the integral of f of x plus g of x dx. So maybe we want to think about this one geometrically a little bit. So if I have some function here which is f of x, and I have some other function, g of x, let's write down f of x here. Maybe I have some other function, g of x. What this is asking us to do is it's asking us to look at the area under the curve where the curve is given by adding f plus g. So if we're adding our red and blue here, it's reasonable that we get purple. And what we're doing is to get the graph of f plus g, we're going to take the y values on f and add them to the y values on g. So we get something that's going to look something like this. Maybe it goes down a little bit there. And then as f of x increases and g of x remains the same, we're going to get some kind of increase. And our function f of x plus g of x looks something like this. And let's go ahead and move this picture out of the way. Cool. All right, so we have our f of x plus g of x here. And what we're saying is we want to compute the area under the purple curve. And it should seem pretty reasonable based on this picture that the area under the purple curve, or the area between the purple curve and the axis, is equal to the area under the red curve plus the area under the blue curve. So if I were to kind of shade this purple region here, in order to get that area, instead what I could just do is take this red area here and add it to the blue area here. So the way we write that out in mathematical symbols is we're going to say that the integral of f of x plus g of x is going to be the integral of f of x plus the integral of g of x. All right, next what we want to do is we want to think about what happens when we're taking some function, and maybe we have f of x, but maybe we want to multiply it by some constant c. So let's again kind of get a picture for what's going on here. If I have my function f of x, and I am multiplying it by some constant c, then I'm taking all of my y values and I'm scaling them by a factor of c. So this is our vertical stretch from 112. If c is bigger than 1, which is the picture that I'm going to draw, all of my y values here are going to increase, and the ones which are closer to the axis increase less than the ones which are farther from the axis. So let's see. So we'll have something that looks a little bit like this, and then we have a large thing kind of growing at the end. So what this ends up doing is if we want to find the area of green, so if red here is f of x and green here is c times f of x, since we've scaled all of my y values by a factor of c, it should certainly make sense that we've taken this red area here and we've increased it by a factor of c in order to get this green area. So what that means is, since right now what this quantity represents is the area under green, that's the integral of c times f of x, we want to write that in terms of the area under red, which is, in this case, c times integral from a to b of f of x dx. So anytime we multiply a function by a constant, it multiplies the area under the curve by that same constant. Maybe think about this one in terms of what happens if I have a negative constant c. Think about why this formula should still hold. Maybe think about what happens if I have a constant c that's less than 1. Again, think about why this formula should still hold, but it certainly is true for all of those cases, even though the picture that I've drawn here is for a positive constant c, which is bigger than 1. The last property that we're going to think about here is, it's not apparent based on this kind of statement what we're going to be looking at, but what I want to do here is talk about if I have a and b here, and what happens if I have some c in the middle? What happens if I have some intermediate value between a and b? And so what I want to think about here is simply the fact that if I'm talking about this red area between a and b here, I could think about it in kind of two pieces. I could think about it in the piece to the left of c, and I could think about it in the piece to the right of c. And certainly the total red area should be the red stuff to the left of c plus the red stuff to the right of c. And so the way that I'm going to break up this integral from a to b is going to be as the integral from a to c. So now I'm using a as the left endpoint and c as the right endpoint of f of x dx, plus the integral from c to b of f of x dx. So what this formula is telling me is that the total area between a and b, which is all of this stuff, is equal to the total area between a and c, the left half of this, plus the area between c and b, which is the right half of this. So certainly this seems reasonable, though it is more useful and a little bit more general than even it looks right now. So right now, the picture that I've drawn has c between the values of a and b, but this need not be the case. Even if c is some value that's way bigger than b, this formula still holds. Even if c is some x value that's way smaller than a, the formula still holds. And it holds because we've kind of defined property b here to be that area between b and a, when you're integrating backwards, is going to be the negative of the area between a and b. All right, so let's go ahead and do an example using some of these properties. So we have some graphs of the functions f of x and g of x here, and we want to compute this integral from 3 to minus 1 of f of x minus 3g of x dx. So the first thing that we need to do is label which function is which, because I forgot to do that. The left function is f of x, the right function is g of x. So if we want to compute this integral from 3 to minus 1 of f of x minus 3g of x dx, one option that we have would be maybe coming up with formulas for f of x and g of x, and then doing kind of this algebraic manipulation here to come up with a formula for f minus 3g, and then drawing a graph of that, and drawing some triangles and some rectangles and computing some areas. That's not going to be the most efficient strategy because we now have these new properties that are going to allow us to do this a little bit more quickly. So the first thing that I want to note here is that the order of integration is backwards. 3 is certainly not less than minus 1, so we're going to need to correct that. And the way that we correct that is to say, well, if we want to flip the order of integration, we need to add a negative sign out front. So this is negative integral from minus 1 to 3 of f of x minus 3g of x dx. So we're a little bit closer now, but we want to talk about areas under f and g rather than areas under f minus 3g. So we'll keep this integral here from minus 1 to 3. But what we want to do is we want to recognize, well, f minus 3g, that's the same as f plus minus 3g. So what we have here is this when we're breaking it, we want to break up this integral into two different pieces here. One where we're integrating f, one where we're integrating minus 3g. And we know that by property, property C here, that when we're taking the integral of a sum, we can integrate the two pieces of the sum separately. So here I've got the integral of f plus minus 3g. So that means that I can integrate f and integrate minus 3g from, again, minus 1 to 3. All right, so the integral of f, well, that's something that we can do right now, though maybe we'll save that for later. Integral of minus 3g, we're close to being able to do. Notice here that we're going to use property D, which says that when you have a constant multiple inside of an integral, it can be placed out front of the integral. So here what we're going to do in one final step, we still have this negative out front. We have the integral from minus 1 to 3, f of x dx. And now we want to bring that negative 3 out front of the integral. So we have minus 3 integral from minus 1 to 3 of g of x dx. So we've taken this problem that we didn't quite know how to do, where we have this integral of f minus 3g, and we've used our properties of integrals to reduce ourselves to the problem of integrating f and the problem of integrating g. And both of those are problems that we know how to solve because we can break things up into triangles and rectangles. So let's talk about the integral of f. We're integrating from minus 1 to 3. So we're going to have a couple of different regions here. Starting at x equals minus 1, we're below the axis, so we want to compute the area of this triangle here. Between 1 and 3, or between 0 and 3, we are going to have a, sorry about that. We are going to have a triangle here and a rectangle here. For g of x, we have a couple more pieces. We're going to have a square here. Above that, we're going to have a triangle. We're going to have another square here. And above that, we have a triangle. We have two more pieces here. We're going to have a couple more triangles. Let's give them, I guess we got to reuse some colors here. We're going to use green and purple. A couple more triangles. All right, so to actually do these integrals here, we're going to want to compute some areas. For f of x, this blue area here is a triangle. It's got base 1, height minus 1, and so its area is going to be minus 1/2. The green area here has base 1, height 1, is a triangle, so its height is positive 1/2. And the red rectangle here has base 2, height 1, so its area is 2. So this integral of f of x from minus 1 to 3, we add up all of these, we add up this blue and this, we add up the blue and the green and the red, and we get 2 for the integral of f of x. So going back to our formula here, we've got minus, this integral we just determined to be 2, minus 3 times something. The integral of g of x, we need to compute some areas here. This blue square has area 1. This green triangle has area 1/2. This black triangle has area 1/2. The red square has area 1. This other green triangle has area 1/2. And this last purple triangle has area minus 1/2 because it's underneath the x-axis there. So adding all of these numbers up, let's see, 1 and 1 is 2, plus another 1 is 3, plus 1/2 minus 1/2 is going to give us 3 still. So the integral of g of x is 3. So moving down here, we can replace this integral of g of x by 3. And simplifying this calculation, 2 minus 6 is going to be minus 4. Taking the negative of that is going to give me positive 4. So all of this said and done, we're able to use some of these properties and some of our geometric knowledge to compute some of these integrals. Next section, we are going to actually take a look at a better way of computing integrals, and we're going to start to see some derivatives show up, and we're going to see how those are relevant.